I'm glad to present Daniel Grimmer, who is going to talk about discrete analogy of general covariance. Could the world be fundamentally set on a lattice?
Yeah, thank you for the introduction. As you said, my name is Daniel Grimmer. I think I met most of you during the breaks, but if I haven't, please come talk to me afterwards. I'd love to meet you all. Right, so I'm a DPhil student at the University of Oxford. Before that, I was a PhD student at the University of Waterloo doing physics. So I've actually just recently switched to philosophy of physics. So I'm a bit new to this topic, but I think I've got some very interesting stuff to tell you all about today. I'll tell you about a discrete analog of general covariance and make a new answer to the question, could the world be fundamentally set on a lattice? Now, Vera told us a bit earlier about Weyl's tile argument, which was actually new to me. It was very interesting to hear about that. But I have a new reason I'm putting forward here about why the answer to this question is no. The world can't be fundamentally set on a lattice. But it's probably not for reasons that you're thinking of. And here, I just put this paper on archive literally this morning. So this is a very fresh archive post for you. If you want to read and get all the details there, I don't have time to talk about everything today. There's really a lot more going on behind the scenes here. Right, so when I'm talking about a lattice, what exactly do I mean? I'm not talking about the sort of discrete theories, or not exactly those sorts of theories that were talked about earlier today by Luca, being like causal set theory or loop quantum gravity or something. I'm talking about very standard sort of lattice theories. But I think a lot of what I'm going to talk about today actually extends over to the quantum gravity applications as well. I mean, and that's the direction I'd like to take this research in the future, right? So just to give you an example of the sort of thing I am talking about, consider the continuum heat equation, which is written up there, which is the derivative in time of some field is proportional to the second derivative in space. And two discrete versions of that, which might be set on either a square lattice or a hexagonal lattice. And here are those equations where you have just nearest neighbor interactions. So I've named them H4 and H5 to follow along with the paper. I talk about lots of different theories there, but we have one that's a square heat equation, which has the lattice site phi indexed n and m changes in this way in time, and so you have the derivative in time being something that approximates the second derivatives in space, at least as well as you can do with nearest neighbors. So I'm thinking about these sorts of lattice theories, and could the world really be that way, and should we take those lattice structures seriously? How should we interpret them if we find that a theory like that works well, right? So what if the world really was like that, right? We would maybe start looking for lattice artifacts, right? Intuitively, the world could be set on a lattice like the kinds I just showed, right? And indeed, quantum gravity seems to point in that direction. I think Luca gave us some reasons why that might be the case, right? So quantum gravity seems to point towards some sort of discrete space-time, maybe not this kind exactly, but something like it possibly. And you might think that maybe by investigating the world on the smallest scales, we go up to high energies and small scales, we might discover that there's some microscopic symmetry restrictions, right? We might only be able to make quarter turns or sixth turns, which preserve our dynamics. So we only have like a fourfold or sixfold rotational symmetry, whereas at the larger scales, we have a continuous rotation symmetry. And you might think those are lattice artifacts, which sort of reflect the discrete symmetries of the underlying lattice, right? And maybe you believe that, and further you want to investigate what kinds of couplings are there on this lattice. Are they nearest neighbor, or next to nearest neighbor, or something longer range or something? And you might think you could go and do microscopic investigations and come to an idea of what that is like, right? So suppose all of that goes very well, and suppose that after a bunch of empirical investigations, we find such lattice artifacts, and we find that, for instance, we have really great predictive success with one particular kind of model, say with a square lattice with not nearest neighbors, but next to nearest neighbor interactions. Suppose all that goes extremely well, and that works perfectly for describing our world, right? Would that prove that the world is fundamentally set on a lattice? We have this extremely successful theory which describes the world basically in those terms, right? Does that tell us that that's the way the world is? No, it doesn't. I think as philosophers we should appreciate this point. All it would prove is that the dynamics of the world can be faithfully represented on such a lattice, at least empirically, right? We have to do extra work to figure out what the world is really like on top of that, right? So anything might be faithfully represented in any number of ways. To use an example of Sam's, I might represent the Earth and the Sun with my fists here and show how they move around in this way, right? So I can represent anything with basically anything, and certain parts of that representation will be good and stand in for substantive things, and other parts will be merely representational and fail to uphold things, right? So we need to do some extra empirical work to know which parts of our representation should be taken seriously, and which parts are substantive and which parts are merely representational, right? So we have now this question, we have an empirically successful lattice theory. Why should we take the lattice structure it seems to tell us is underlying the world? Why should we take that seriously, right? And I think we all have some strong first intuitions about this. And so why would we take this lattice structure seriously? All these three claims I'm about to make seem highly intuitive. It seems like the lattice structure restricts our symmetries. It seems like a theory that set on a square lattice could only have the symmetries of that lattice. Discrete shifts, quarter turns, and some mirror reflections, but not others, right? And similarly for a hexagonal lattice with 1/6 rotations, right? So it seems like the lattice is doing a job of restricting our symmetries. And similarly, it seems like the lattice is doing a job of distinguishing the theories, right? Two theories with different lattice structures couldn't possibly be equivalent to each other because they have different symmetries and they have different underlying spacetimes, and it seems like they really can't be the same theory, ultimately. And it seems, moreover, like the lattice is just plain fundamental. It seems like it's a fundamental part of the theory. It's what the fundamental fields are defined over. They take lattice sites and possibly times and then map them onto real numbers or temperatures or something like that. And they play a non-eliminable role in capturing and determining the theory's symmetries. It seems like these lattices which are in the theory, they don't seem like they're merely representational. They seem like they're really baked into the theory, right? And I'm stressing this so hard because none of that is true. Absolutely none of that. And I hope to convince you that with this. And I really spell this out in the paper in quite a lot of detail. So I develop and argue for a very rich analogy between the lattice structures that appear in our discrete spacetime theories and coordinate systems which appear in our continuum spacetime theories. So lattice structures are a discrete version of coordinate systems. That's what I'm putting forward here today. And that analogy is confirmed in three ways, which disagree with those three intuitive points I just raised. Neither lattice structures nor coordinate systems restrict our symmetries, right? Theories set on a lattice, in fact, can and do have continuous translation and rotation symmetries, despite the fact that they're representable on a lattice, at least, right? And this is in the same way that coordinate systems don't restrict our symmetries. We can have a rotation invariant dynamics described on Cartesian coordinates. There's absolutely no reason that the symmetries of the coordinate system have to match with the symmetries of the underlying mechanisms, right? It might be nice if they do, but there's no reason they have to. A second way that, that supports this analogy is that both are interchangeable, right? We can have a theory with one coordinate system and describe it with another coordinate system. There's no issue there, right? The same thing's true of lattices. You give me a theory described on some lattice, a square lattice, I'll give it back to you, an equivalent version described on a hexagonal lattice. I can switch between lattice structures at will. And I'll show you how that works in the later part of the talk. And ultimately, both are optional, right? You give me a theory described on some lattice, and I can always reformulate it for you in a way which references no lattice at all. And this is analogous to giving a continuum theory a generally covariant formulation or coordinate-free formulation. And this is why I'm talking about a discrete analog of general covariance, right? So I've got something similar that works in the discrete setting. And again, in the paper, I argue for this quite a lot, but here I just have time to present the analogy and some of its consequences. I have, though, a lot of arguments for it. So ask me about that later if you like. But the proposed analogy is here. We have on the left coordinate systems, changing coordinates, and a generally covariant formulation. And these are analogous with the things on the right. Lattice structures, as I already said. The other two things I don't expect you to understand at the moment, the Nyquist-Shannon resampling and band-limited formulation, which is supposed to be somehow a lattice-free reformulation of the theory, right? But in order to understand the terms on the right-hand side, I'm going to need to explain and introduce some mathematics, the Nyquist-Shannon sampling theory first. But roughly what this theory does is it gives us a dictionary to translate between discrete and continuous descriptions of a certain class of mathematical functions, namely band-limited functions, right? So consider the following function f here, which has a special property of being band-limited. I'll explain what that is in a second, but let me explain first what it does, right? So as a consequence, this function f can be reconstructed exactly everywhere. There's no approximations going on with anything I say in this talk. it can be reconstructed exactly and everywhere knowing only some of its values, right? So in particular, suppose we know this function only at these half-integer values, xn equals n over 2, right? Now, because FB has this special property of being band-limited, this is all that we need in order to recover the function exactly. So to recover FB, what we do is we first take any of those sample points and we associate it with some sync function, which is sine of x over x, but shifted and rescaled to fit the diagram in the way put over there, right? So we associate a sync function with each of these points. We do that for every point, and then we add all those functions together, and this gives back the original function FB exactly with no approximation whatsoever, as long as the original function was band limited, right? Right? So that's the sort of Shannon-Nyquist sampling theory in a very, very basic way. But what does it mean for a function to be band limited? In terms of mathematics, band-limited functions are those which have no high-frequency content. A band-limited function is one whose Fourier transform has compact support, meaning that the Fourier transform only has support for wave numbers k less than capital K, right? So there's some bounded support for its Fourier transform. And the original function before was this function. S is the sync function, remember. So it's some construction there, but the bandwidth here was k equals pi. Right? So I chose it so that the bandwidth would be pi. That's the extent of the frequency support. Right? So what was the equation then for the reconstruction? If you have some function, some values fn at the points xn, then the reconstruction formula is this one. You take those values, multiply them by some sync functions, shifted and scaled as appropriate, then you add them all up, and that gives you the exact function back, so long as the lattice points are sufficiently dense here, meaning that the spacing is less than some critical spacing, which is pi divided by the bandwidth, right? So this is the sum of shifted and rescaled sync functions that I showed you before. So here's another example. Because k was equal to pi, the critical spacing here is just 1. So I did a spacing of 1/2 last time. I could go down to 1. And so here's a spacing of 1, and it's shifted by 1/3. That works just as well. To recover this function, you do the same thing. Sync functions, scale them up, rotate, shift them around, add them back, and you get back the original function with no approximation. Right? So that's the Shannon-Nyquist theory on a uniform lattice. But the real magic of this stuff is that it works on any sufficiently dense non-uniform lattice as well. Right? And let's see how that works. Consider this function here, which I've sampled every 1/4. Right? So in some sense, there's 4 times too much information in the sample values. I could drop 3/4 of that. There's no reason I have to drop those sample points uniformly. I can drop them in a non-uniform way, have this non-uniform sampling, and from here, I can do the same process, although it's more complicated, and reconstruct from there, as long as they're sufficiently dense in some sense, right? So I associate to each sample point some function, then I do that for all the points, and then I add them up, and this gives back the original thing with no approximation, right? And so I can recover things from non-uniform sample points as well. And the same story is true in higher dimensions. Here's another band-limited function. It's J1 is a Bessel function. Don't worry about what the math says, but it's band-limited with a bandwidth of k, right? And so the following figures I'm going to show you are all different ways to represent that, which are equivalent. Here it is represented as a band-limited function. Here I can sample it at every half integer. Here I can sample it at every integer in both directions. Here I could do that on a rotated set of coordinate systems. Here I can sample it on a hexagonal lattice just fine and reconstruct from there, just a different reconstruction formula. And here I could represent it on a non-uniformly sampled lattice and reconstruct it from there with no issue and no approximation at all. Right? So that explains the terms on the right-hand side. So coordinate systems are like lattice structures, I'm saying. Changing coordinates is like Nyquist-Shannon resampling. So you give me your theory in square coordinate, in a square lattice. I'll create a band-limited function from that, sample it onto a hexagonal lattice, carry across the dynamics, and get an equivalent description of your theory in a hexagonal setting. Right? And I can do this between any lattice, irregular or whatever. But then the process of going into a coordinate-free representation, or in the analogy, a lattice-free representation, is to redescribe your physics in a band-limited way. Right? So that's all just mathematics. Let's apply that to some physics and see what happens then. So here, consider the 1D nearest neighbor heat equation here. In order to associate that with some band-limited function, there is no space-time going on behind the scenes here. There's just the lattice points. And I'm not assuming they're embedded in any space, right? So there's just the lattice points floating out. I need to invent a manifold and then embed these onto the manifold somehow, right? And I talk about in the paper how we have really great freedom in how we pick which manifold we want to embed onto and how we pick the embedding onto that manifold. But let me just pick something very simple here. The simplest thing you might do is invent a space-time here, which is two-dimensional, and put the sample points in it in this way. So z minus 4 up to z4, moving just through time uniformly with even spacing between them. You could choose other things, but this is what I'm choosing to do here, right? And then so you then invent a band-limited function phi b, which has at these sample points at those times the values that our discrete field did, right? And so then from this embedding, what we can do is reconstruct this field phi b here by using this sync reconstruction formula. And so we're translating our discrete dynamics over onto a manifold description. And this is a one-to-one mathematical move, right? So using that embedding, that embeds a state over onto the thing, but we can also take the dynamics and translate it over. So we have this 1D heat equation here, and using the fact here that translation, so h of x plus a is equal to the exponential of the derivative operator applied to the function, right? Using that, and don't worry about the calculation there, the point is just to show that you can take that discrete dynamics and translate it over into the band-limited setting. And what you find at the end of the day is this, that the derivative in time of this band-limited field is proportional to some operation, some differential operation on the field, right? But it's not the continuum heat equation. It has this hyperbolic cosine of A derivative, not just the derivative squared, like you might have expected. But, however, note that if you expand that hyperbolic cosine for small a, you get back the second derivative plus a to the fourth terms. So in the continuum limit, this thing does behave like the second derivative if the scales are appropriate, right? So we do get back the continuum heat equation in the continuum limit as we expect to, but we have an exact description in continuum terms outside of that limit as well, right? And if you do that same thing to the other two heat equations I talked about before, the square one and the hexagonal one, you find these are the differential equations for their band-limited fields, right? And something to notice is that all three of these dynamics here in the band-limited case written on the screen are translation invariant, right? But none of them are rotation invariant, unfortunately. And I stress this in the paper. These theories had this translation invariance all the time, right? It's not because I put them onto a continuous manifold that they suddenly get this continuous translation symmetry. They always had it, independent of whether I put it on a manifold or not. Right? I just don't have time to go into that now. But it's not a trick because I'm putting things on a manifold that they suddenly get new symmetries. The symmetries are the same as they always have been. Right? And I can say a lot more about that after the talk if you like. But that's a very important thing to note here. Right? So I have these two ways of describing the system, one in terms of a band-limited function and one in terms of discrete samples thereof. And these continuous and discrete descriptions exactly match each other in the following sense. Say I have this heat distribution initially at the start, and then I choose to sample it on a square lattice, and then I can evolve that forward with the square lattice dynamics with this top line here. That would evolve it forward in some time into the third panel. And then from that, I can reconstruct it into a band-limited function at the end of the day, right? Now, the connection from the first picture directly to the fourth picture comes by evolving via this differential equation here in terms of the band-limited function, right? So these are really just two different ways of describing the exact same thing. And the same is true for the hexagonal heat equation here. I can have this discrete description of it, or this continuous description of it, and they interact with each other in exactly the same way I said before. If you sample, evolve, and then reconstruct, that's the same thing as just applying the differential equation directly from the start to the end. Right. Okay. But so far, what I said, actually, if you look at the diagrams carefully, it seems to support that the lattice structure seems to be having an effect on the symmetry of the dynamics. If you look at this, the symmetries of the lattice, in this first picture I sampled on a square lattice, and if you look closely at the final state, it's not rotationally invariant. There's a square distortion to it, right? And the same thing in the second picture, there's a hexagonal anisotropy there in the second picture. But that's just a coincidence, and that's not always the case. In fact, here, and I worked this out really explicitly in the paper, all of these three evolutions I'm showing here are evolutions by that square heat equation, right? So I can describe it on the square lattice like I'm doing on the top line, and I get this square distortion at the end of the day. I can also describe it on the hexagonal lattice and get that same square distortion at the end of the day. And I can even do the same description on an irregular lattice, right? So the way that we're representing the dynamics on which lattice we happen to choose to represent it on has no effect whatsoever on the symmetries of the dynamics or the symmetry of the final state, right? And the same thing's true for the hexagonal thing. I can get the hexagonal dynamics. I can describe this equally well on a square lattice or a hexagonal one or an irregular one. And in fact, and you ask me about this later, I don't have time for it now, but you can even do rotation invariant dynamics on these lattices, right? So there's another sort of dynamics that I haven't shown you yet, but I can have extra slides about it if you want, where the final state comes out rotation invariant. So you can have rotation invariant dynamics described fully well on any sort of lattice you like. So there's no effect whatsoever of a particular lattice structure or representational choice of a lattice structure on the types of dynamics that we can describe, right? So here's the conclusion. Our pre-theoretic intuitions about lattice structures were that they restricted our symmetries, that they distinguish different theories from each other, and that they're fundamental. Right? As I've discussed here, none of these conclusions, none of these first intuitions are right. Actually, they do not restrict our symmetries. Theories set on lattices can and do have continuous translation and rotation symmetries. They're interchangeable. You give me some theory described on one lattice, I will redescribe it for you on a different lattice and give it back to you. And that process is actually as easy as switching coordinates. And thirdly, they're ultimately optional. Given any theory described on the lattice, I can always reformulate it to reference no lattice at all. And this is reformulated using band-limited functions. And these 3 points are exactly in line with how coordinate systems behave. And I think this establishes a very rich analogy between the lattice structures that appear in our discrete space-time theories and coordinate systems which appear in our continuum space-time theories, right? So again, here's the analogy that I proposed. Coordinate systems, like lattice structures, changing coordinates is like resampling in a band-limited way, and rewriting things as band-limited functions is the discrete analog of general covariance, right? And we can describe any band-limited dynamics on any lattice just as we can represent any band-limited state on any dynamics, right? So the main lesson to take away from all of this is that lattice structure is less like a fixed background structure or an underlying manifold, and it's rather more like a coordinate system, meaning it's really just a merely representational artifact, at least if we take this analogy seriously, right? And so this has a lot of consequences for the philosophy of space and time. Well, the lattice structure supposedly underlying any discrete lattice theory, really, if you believe this analogy, has the same level of physical import that coordinates do, which is to say none at all, right? Coordinates are not important in our dynamics. You can describe any situation using any coordinates you like. You don't go to the coordinates to try and get physical understanding of your theory, of what it's substantively claiming that there is in the world, right? And thus, I'm claiming that the world can't be fundamentally set on a square lattice, or any other lattice for that matter, any more than it could be fundamentally set in a certain coordinate system. It might be most conveniently written in a certain coordinate system. It might, be stupid not to describe it in all but one coordinate system. But that doesn't mean that that is a substantive part of your theory. Because like coordinate systems, lattice structures are just not the sorts of things that can be fundamental, right? They are both thoroughly representational, as I'm putting them forward, right? And so my final conclusion here is that space-time can't be discrete, even if it can be represented as such. You may have your favorite description of the world, which involves a discrete description of things happening in your space and time. I'm going to analyze your theory and interpret it for you and show you that really it doesn't have the properties you think it does. It's really much more intuitive to interpret it as a representational artifact. And so I don't think your discrete theories are really discrete when properly understood, right? Right? And there's another set of consequences regarding this. The band-limited physics could be represented on either a continuous or a discrete setting, right? So when the physics is band limited in this way, it simultaneously has representations which are discrete, and it has representations which are continuous. And so it can sort of switch camps between the two. And what this seems to do to me is it undermines sort of the substantive nature of the manifold, right? The space-time manifold no longer, in these theories at least, seems to be so descriptively essential, because we have fully accurate descriptions of the physics which take it completely off of the manifold, right? So we can take our physics off the manifold, invent a new manifold to put it onto, and the manifolds in a way can switch out just as well as the lattice sites do. And so it seems like the manifold, in these theories at least, is just a convenient representational tool and not anything fundamental, right? And sure, that's not true when the physics is not band limited, right? When the physics is not band limited, then the manifold still does seem descriptively essential. Because if you have arbitrarily high frequencies, you can make step functions, and you can make point functions, and you can make the delta function, and you can localize things arbitrarily with infinite frequencies, right? You can't do that with a finite set of frequencies. But anyway, so the manifold still might be descriptively necessary when the physics is band limited. But that necessity is sort of contingent on the physics not containing arbitrarily high frequencies. If the physics was band limited, then we wouldn't need so much of a manifold to describe it, right? So it's just because the state of the world is in such a way that it contains arbitrarily high frequencies, this is what makes the manifold necessary in a descriptive way. Whereas if the world wasn't like that, the manifold wouldn't be so necessary, at least descriptively, right? And so I don't know what this says about the fundamental nature of the manifold, but it at least seems in some ways contingent on what it's holding up, right? So thank you for your attention. If you have any questions, I'd be happy to take them. Yep.
Thank you very much. So we have 10 minutes, even with the 15 if we count the 5 minutes.
Sorry, this isn't working. It kind of works, but it's not ideal. Is that better? Sort of. All right. Thanks so much. So usually when we declare that something is a coordinate system, we have a pretty good grasp of what physical structures say, what geometric structure underlies it. So that, for example, when we go from one coordinate system to a different one, we preserve that structure. So, you know, we have Cartesian coordinates, and underlying that is Euclidean structure, for example. What would be the structure underlying these shifts that you have in mind from one lattice representation sampling to another? Do you have a grip on this? Like what is the common physical, geometric, or something content here that is being preserved or that we are characterizing equivalently in terms of these different lattices? Thank you.
That's a great question, and I just started.
Okay, so I really like this way of thinking about lattices, like something like coordinate systems. But you're saying that they're not fundamental somehow in the description of the theory, right? So I was thinking there are some people in quantum gravity who would say the opposite. So some people in quantum gravity would say that spacetime is fundamentally discrete, that, you know, this is a property of nature. So how would you respond to that?
I disagree with them.
Okay.
Actually, in the paper, I only ever apply the stuff to the Gauge equation. But I'm absolutely convinced it applies to the Fine-Gauge equation as well. Right? So I can do this in Lorentzian space-time and Lorentzian stuff as well. There's nothing in here forbids me from doing this all with relativity. I haven't applied it to. I haven't applied it to any quantum gravity stuff. My conclusion at the end doesn't disagree with them. Space-time can't be fundamentally discrete, even when it's representable as so.
That's right. That's right.
I think they may have valid descriptions of what's going on in there. I think if I do some interpretive work on that theory, I might be able to re-describe it in a way where that course of lattice structure is course of coordinates.
Yeah, this is very, very interesting actually, because you say very strongly that the space-time cannot be discrete, right? So this is in a very strong opposition to some of these claims when, yeah.
Mm-hmm. If you have a strict representation, they may be useful, they may be insightful, they may be fit to the situation very well, or whatever. But if they are just so representational, right, and we do have so many choices for how to represent things in this way. And when you really see the full catalog of different discrete representations, it seems like, well, why are you picking one of them rather than another? So it may be a good description, it may be a very useful pragmatic description, it may be the one which we discovered does very well. My argument is not fundamental description.
Okay, thank you. So just to, well, I mean, I don't know these arguments that well, but I understand that, you know, people are making arguments in quantum gravity why the spacetime has to be discrete. And I guess then one would have to understand those arguments as arguments saying that the particular description has to be discrete rather than, you know, the fundamental structure, right? So.
Yeah. So when my strategy would be to go reread all of their arguments, and whenever they argue it has to be discrete, I would replace that with it has to be representative as discrete.
Yeah, okay.
And I think their arguments probably will just the same.
Same, yeah, I believe so.
Physicists often don't, they argue things have to be a certain way, they really argue things have to be representable in a certain way. And we need to do more work past that to find out what it's really like. The role today, really likely to me that the world is discretely representable, but it can be fundamentally.
Thank you. Thanks a lot.
Very interesting. I learned a lot from this, but somehow what you're claiming here seems to be in contradiction with what's going on in quantum field theory. When you are considering discrete quantum field theory, the features of that theory, by which I mean on a lattice, then the features of that theory seem to be radically different from the features of quantum field theory on a real four-dimensional space-time. So radically, in fact, that I cannot imagine that the same kind of equivalence which you displayed here in connection with these terminology, bandwidth functions, would hold in that situation in which you assign not a function, which you're considering not a function just on the lattice, respectively on a continuous space, but more complicated objects. And I'm wondering whether in that particular situation, the same claim you would regard true and whether it is true or not.
What differences are you have in mind? Because the differences could come from several places. With this band-limited description, what you're doing is you're cutting off the UV. Right? The Fourier transform only has support in a compact region. So if the UV structure of the theories are different, that's absolutely a part of this. So I'm just talking about band-limited physics, where we don't have that UV structure, and that's cut off entirely. But if it's about loss of symmetry, if it's about introducing rotational artifacts because of a square hexagonal lattice, that's something you can completely get over. That's something, a lattice theory and setting your theory on the lattice and breaking all the continuous symmetries, those don't have to go together. There's fully ways to do that. So I'm not sure which parts are doing. I should mention there are a few groups of physicists doing Bandlimited quantum field theory. And sort of looking at this from a pragmatic perspective as it relates to lattice QFT, but also from a fundamental perspective for reasons of quantum gravity. We think that space stops making sense at a certain scale, or things stop having support at a certain Fourier transform degree. But what did you have in mind? What did you do?
Well, I had in mind associating with regions of the discrete lattice for Neumann algebra, for instance, and the same thing in a continuum space-time. And then if they are covariant, they are quite different. The type of the algebras are really radically different, and they cannot be isomorphic. So this is what I had in mind in particular, and this is a bit more complicated as an object, more complicated than a bandwidth function. So I'm wondering if the same kind of argument might go through in that case. It might, but I think the intuition is, I think, on the part of the physicists that it is not possible. So it's really an interesting issue.
Yeah, again, I know people who are doing Bandlimited quantum field theory, and I want to work in that direction. I'd like to really work on that and move in that way. But I think you can do at least big parts of quantum field theory in a Bandlimited way, but I'm not doing the details yet.
Maybe very quick, we still have another question.
Sure. So I'm curious about whether this is really an argument that you can't make sense of space-time being either continuous or discrete, whether you think that distinction doesn't make sense. Because it looks like there's some kind of argument here. There's a kind of underdetermination. We can get exactly the same information on a discrete structure or continuous structure. Is it actually an argument that space-time can't be discrete, or that attributing discreteness or continuity to space-time isn't something the physics is going to specify for us?
Yeah, I sort of think the latter half is the direction I'm leaning. So definitely, when things are discretely representable, they're discretely representable in any number of ways, right? And the choice between that is equivalent to a choice of coordinate systems in my mind, right? I don't think when things are discretely representable, that's not fundamental. But when things are discretely representable, the manifold seems like too much. Like, why do you need this whole continuous manifold? If things are discretely representable, why do you have a continuous manifold? That also seems like too much, right? And so the manifold, and I've stressed throughout this talk, when I put these theories on a manifold, the manifold's an invention. So I'm sort of liking to embed this thing on, to get my intuitions about locality going, or something like that. You know? So the manifold seems like it's too much, and the discrete representations seem like they are, there's too many of them available to us for any one of them to be fundamental. And so I mean, what I say is space-time can't be discrete. It's possible space-time can't be discrete. Also, space-time can't be continuous. Space-time is not fundamental. You know, that's the, so space-time just maybe space-time itself is just representation. In the same way that lattice structures and coordinate systems are. It's all just representation.
Thank you.
But then there's not much left in the theory. I mean, I don't know what the theory is about. It's not about fields on a space-time. I don't know what it's about anymore.
Thank you. Yeah, very interesting stuff. I actually had the very same question that was just asked, but I have just a tiny other question as well. Do you think that there might be some sort of ontological parsimony argument in favor of a discrete space-time? Because, I mean, if you say that fundamentally there's no fact of the matter, actually, about whether space-time is discrete or continuous, so if you lean towards that direction, then clearly there can be no such argument. But you didn't seem so decided, let's say, between saying that it cannot be discrete and saying there's no fact of the matter. Yeah. Yes, so I was wondering, if we assume that there is a fact of the matter, metaphysically speaking, whether space-time is continuous or discrete, because you didn't seem to rule this out completely in response to the last question.
If I'm pressed on that, there has to be another status about continuous and discrete, I think we're continuous.
Okay.
Because it gives a more adequate representation of the symmetry of the theory. Right? The theory, like I stressed before, where you just think discretely, it still has the continuous symmetries, even when you represent it discretely. But the way to make sense of that is some sort of internal symmetry. right? And if you want those to be external symmetries and be very intuitive, and to give you better intuition about locality, if I'm pressed, I lean towards pretty elemental.
Okay, I see. Thank you.
That's one question for another like.